So far we have seen Cauchy's theorem, Cauchy-Gorsa theorem, and some of its generalizations. Now these results help us in simplifying and evaluating some of the complicated contour integrals, and other applications of these results include simplifying a contour integral and, most importantly, proving that an analytic function has an entire derivative. Now let's have a look what is a Cauchy's theorem. So Cauchy's theorem is if a function is analytic in a simply connected domain D and f prime is continuous, then the contour integral around any simple closed curve is 0. And this was introduced by Cauchy in 1825, and later on in 1893 Gorsa generalized this result and showed that we don't need the condition of f prime is continuous and prove this thing. We have seen these results, we have seen how to apply these results, and we have seen some of its generalizations, which are some of the important results of complex analysis. Now in this module we are going to start the main results in the theory of complex valued functions, known as the Cauchy integral formula. Now what is Cauchy's integral formula and why it is important? So in simple words, Cauchy integral formula gives us information about the functional values which lies inside the contour by just using the functional values which are on the contour. So by using functional values on the contour, we can find the functional values which are inside the contour. So let's have a look what is Cauchy's formula, integral formula. So if a function is analytic in a simply connected domain D and C is a simple closed positively oriented contour that lies inside this simply connected domain D, and if Z0 is any point that lies interior to C, then the functional value of f at this point Z0 can be calculated by using the following formula, which is 1 over 2 pi iota and this contour integral of f of z over z minus z0 dz. So this functional value is given in the following way: 1 over 2 pi iota and this contour integral f of z over z minus z0 dz. So z0 is any point inside or in the interior of this contour C. So we can choose this point to be any point inside this, and the functional value can be found using this formula, and hence the statement that all of the values that lies all of the values for the points that lies inside this contour C can be found in this way. Now let's see how to prove this formula. Now if f is analytic function, we know that if a function is analytic, then it is also continuous, and since it is analytic at each and every point of D, so of course it is continuous, and it is analytic at Z0 since Z0 belongs to D, and hence it is continuous at this point. And from our discussions on continuity of complex valued function, we know that if a function is continuous at a point, then for each epsilon greater than 0 there exists a delta greater than 0 such that this distance is less than epsilon whenever this distance is less than delta. Okay. Now moving on, we impose a further condition on this delta, that delta is such a small entry that this circle with center Z0 and radius delta by 2 lies inside this contour C. Okay, so now here you can see this circle, and of course you can also see its orientation. It is positively oriented and the radius is delta by 2, the center is Z0, and it lies entirely inside this interior of contour C. Okay, so that's what we have achieved so far. Now let's recall a result that we have proved in our previous discussions. So the contour integral of 1 over z minus z0 raised to power n is equal to 2 pi if n is equal to 1, and it is equal to 0 if n is not equal to 1. Okay, now we are going to use this result. Now using this result, and we can write down f of z in the following form. So f of z0 divided by 1 over 2 pi and this contour integral. So why this equality hold? Because we know that this quantity is equal to 2 pi iota, and this 2 pi iota and 2 pi iota will cancel out each other, and we will be getting f of z naught. Okay, now since f of z naught is a fixed complex number, so it's going to be a constant, so we can write it down inside this integral sign. Okay, and it will be a simple task. Okay, so now let's have a recall from another result that we have discussed in our previous discussions. So this is the deformation of contour. If we have a if we have a domain D and we have two curves C1 and C2 which are simple and closed, positively oriented, and if f of z is analytic in a domain D that contains both C1 and C2 and the region between them. Okay, so over here you can see the domain D, so it is analytic inside this blue shaded region, and the blue shaded region contains C1 and C2 and every other point between C1 and C2, and if this holds, these conditions hold, then the contour integral along C1 is equal to the contour integral along C2. Now using this result we can write down this contour integral in the following way. So the contour integral of f of z over z naught along C is equal to the contour integral of f of z over z naught along C naught, because C and C naught, so C naught is contained inside C, so C naught is a circle with center z naught and radius delta by 2, and it is contained inside this contour C, and that's the reason why we imposed the condition on delta such that C naught lies inside C. And due to this condition and the condition that function is analytic throughout this domain D, and this domain D contains both of these contours, so that's why we are able to apply this result of deformation of contour, and these two contour integrals are equal. Now using this equality and this equality, we are going to move further in our result. So let's see how we move on. Okay, so now consider this expression. Okay, now remember, what do we want to prove? So we want to prove that this functional value f of z naught is equal to this contour. Okay, so this contour integral 1 over 2 pi iota contour integral of f of z over z minus z naught. So that's what we want to prove. Okay, so to prove this equality, we use a very basic trick of analysis. So in other words, we want to show that the distance between these two quantities f of z naught and this contour integral is as small as we want. So it is less than some number epsilon, and epsilon can be as small as we want, and hence these two quantities are equal. Okay, so moving on, so this remains the same, so this contour integral remains the same, and f of z naught, as we have observed that it is equal to 1 over 2 pi iota f of z naught over z minus z naught dz. Okay, now moving on, using results from contour integral. So this mod sign, so if we take this mod sign inside the contour, then there will be this less than or equal to sign. Okay, so this is less than or equal to 1 over 2 pi iota, and this mod sign when goes inside, so it becomes modulus of f of z minus f of z naught. So this is f of z, this is f of z naught. Okay, and then the denominator of both these quantities is the same, z minus z naught. So we have the modulus of z minus z naught, and then we have this quantity dz, and so we have the modulus of dz. Okay, so that's what we have achieved so far. Now the point is this distance f of z minus f of z naught, the modulus of this, so it is less than epsilon. Okay, so we are getting this result because the function is continuous. Okay, so 1 over 2 pi remains the same. Now let's talk about this result. Now this z, okay, so lies inside this circle C naught. Okay, so because we are taking integral over C naught, so that's why the distance between z and z naught is less than or equal to 1 over 2 delta. Okay, so and then we have this modulus of dz. So in other words, when we calculate this thing C naught dz mod. So we get the circumference of the circle, which is 2 pi r, and in this case the radius is delta by 2, so we get 2 pi delta by 2, and using some cancellations, okay, so this delta will be cancelled out with this delta, and 2 will be cancelled out with this 2, and this 2 will cancel out with this 2, and this pi will cancel out with this pi. Okay, so what do we get? So we get the following expression, that this is equal to epsilon, and epsilon is arbitrary, as you know from the definition of the continuity of complex valued function. This is as small as we want. So in other words, we can say that this distance is equal to epsilon, and epsilon is arbitrary. It could be 0.00001, it could be as small, as close to 0 as we want. So if this happens, then we can say that this quantity is in fact approaching to 0, and hence 0, and if this quantity is equal to 0, then we have our Cauchy's integral formula. Now let's consider this contour integral dz over z. Now we have seen this contour integral in our previous discussions. Now what was the major issue in evaluating this contour integral? Now in this case, this contour is a circle oriented in the positive way, and the point is we used basically fundamental theorem of integration to evaluate this thing. And what was the major trouble there? So the major trouble was the entire derivative of 1 over z is log z, and we know that log z is not differentiable along its branch cut, and in this case, since C is a circle, we can change the branch cut, but in this case we cannot avoid the branch cut, since it is a circle and it will take a complete round of this origin. Okay, so whatever branch cut you choose, you cannot avoid this scene, you cannot avoid this case that log z, we have log z, and it is not differentiable along the branch cut. Okay, so to avoid this situation, what did we do? So we divided this circle into two parts. So we divided in the following way. So let's say this is C1 and let's say this is C2, and then we divided this contour integral into two contour integrals, and then we evaluated these contour integrals using fundamental theorem of integration. Now this was a kind of complicated task. Now in this case, we will see that Cauchy's integral formula will help us in evaluating this contour integral in an extremely simple way, and of course it will show the power of this integral formula. Now if we want to apply Cauchy's integral formula, then we need to compare this form with the form that appears in the Cauchy's integral formula, which is f of z over z minus z naught. And by comparing, what do we get? So f of z is f of z is 1, this constant function, and z naught is 0. Okay, and hence by Cauchy's integral formula, this becomes 2 pi iota. So remember, in the Cauchy's integral formula we have 1 over 2 pi iota over here, but we can just multiply it on the other side. So we get 2 pi iota f of 0, and this function f of z is a constant function with value 1. So f of 0 is going to be equal to 1, and hence in this case this contour integral is equal to 2 pi iota. And remember from our previous discussion when we were discussing this fundamental theorem of integration, that the value of this contour integral was 2 pi iota, but we calculated it in a very complicated way. So that's one of the use of this Cauchy's integral formula. Now moving on to another example, we have this polynomial of degree n in the numerator, and in the denominator we have z minus alpha dz. And now we want to evaluate this integral. Of course, with reference to the context, we are going to apply Cauchy's integral formula. But let's for example, for a moment forget that we are in the section of Cauchy's integral formula, and let's try to evaluate this contour integral. Okay, now the point is this contour integral cannot be equal to 0, because this integrand is not an analytic function, because this alpha lies inside this contour C, and there is z minus alpha in the denominator. So Cauchy's-Grosset theorem does not cannot be applied here, and according to that result it is not equal to 0. And the next thing that compel us to apply Cauchy's integral formula is its form, because it is analytic function divided by some linear function of the form z minus alpha, which is very similar to the form that appears in Cauchy's integral formula. So to evaluate such contour integrals, we always prefer Cauchy's integral formula. Okay. Now let's see if the integrand satisfy all the conditions of Cauchy's integral formula. So over here, this polynomial, it is an entire function, so it is analytic at each and every point in the complex plane, and we can take the domain D to be complex plane, and we also know that complex plane is a simply connected domain. So these two conditions are satisfied. Now moving on to the next condition, this contour C is simple and closed and positively oriented. You can see from this diagram that it is anti-clockwise oriented, so that's why it is positively oriented, and hence we can use this Cauchy's integral formula in the following way. So 1 over 2 pi iota Pn z divided by z minus alpha is equal to Pn of alpha. Okay, and if we multiply 2 pi iota on the other side, so we have the value of this contour integral is equal to 2 pi iota Pn of alpha. Now this Pn of alpha may or may not be 0. So how do we evaluate this Pn of alpha? Just replace the value alpha in this expression of the polynomial and you get this Pn of alpha. Now if this expression is 0, what does it mean? So it means that alpha is 0 of this polynomial, and if alpha is 0 of this polynomial, then this polynomial contains the expression z minus alpha, which will be cancelled out with the denominator, and we will get a polynomial of degree n minus 1, and polynomials are analytic function. And so if alpha is a root of Pn, or if this expression is 0, then this expression, this contour integral is 0 by Cauchy-Grosset theorem. Okay, so that's how these Cauchy's integral formula is kind of generalization of Cauchy-Grosset theorem. Now in this module we have seen one of the main results of complex valued functions, which is the Cauchy integral formula. Now in this Cauchy's integral formula, we have seen that if the contour integral is not equal to 0 by Cauchy-Grosset theorem, so if function is not analytic, then what are the scenarios, or in other words, we can now apply this Cauchy's integral formula to evaluate contour integrals where integrand is not analytic. But of course it has some special form that we need to check to apply this Cauchy's integral formula. Okay, so in some sense we can say that this Cauchy's integral formula is a generalization of Cauchy-Grosset theorem. And this Cauchy's integral formula has many useful applications that we will see in our future discussions.